Good day, my name is Philip and you're welcome to Chemistry Class Notes. So today we're going to be looking at your waec chemistry practical questions. I think your practical should be coming on the 14th of this month. So this video is for those taking the chemistry practical, waec of course. And I'm going to be looking at titration and your salt analysis. So for the titration, we're going to look at this 2019 question. Is almost the same specimen that was brought. That is the titration is between sodium thiosulfate and iodine. So that's why I choose this particular question to explain this titration. Take notes. This is just to guide you. I will also put out the table. We'll do some calculation, but the figures are made up. They are made up figures so that you can use for your revision. All right. This is 2019 waec chemistry question. So for me, you can see that they said A is a solution containing 15.8 gram per dm cube of this sodium thiosulfate. Then B was obtained by dissolving 9.0 gram of an impure sample of iodine in aqueous potassium iodide, and the solution made up to 1 dm cube. The normal procedures. A. Put A into a burette and titrate it against 20 or 25 cm3 portions of B. Use starch solution as indicator. Then discontinuation. Repeat the titration to obtain concordant values. Tabulate your results and calculate the average volume of A used. This is the equation for the reaction. Then from your results, calculate the concentration of A in mole per dm cube, concentration of iodine in B in mole per dm cube, then percentage by mass of iodine in the sample, then the atomic masses of oxygen, sodium, sulfur, and iodine is given. After the calculation, I will also answer some follow-up questions. So you can always go back to the first page to see the questions again. So from what we were given, let's draw the table and solve some questions. But take notes, this is the equation. This is an ionic equation. It's the same thing as the equation, right? So yeah, I can put Na here, Na. Sodium will be in these three places. If you see sodium there, it's the same thing. Don't let it confuse you. This is just an ionic representation of some part of the equation. So let's draw a table and answer the question. So from here, you can see that I've drawn out the table. Right? Remember, I didn't carry out this experiment or the titration. I'm just using these values to explain that question and solve the questions I was giving. So when you're drawing your table, as usual, you know how to draw a table. But the way I would like to do my own, after drawing the table, I will put the volume of the pipette 25 cm3. Right? Then the indicator you are using is starch. Then before I draw this side, first, second, you can do third, right? Then burette readings in cm3, final burette readings, initial burette readings, all in cm3. I think everybody knows this by now. So when I start, remember your thiosulfate will be inside your burette, while your iodine, you have to pipette iodine. Your iodine is golden brownish. It has a golden brown color. That is iodine. The thiosulfate is colorless. It's one that will be inside your burette. Then when you start titrating, your iodine will be inside a conical flask. then you start titrating. Remember, you don't add the saturation yet, right? As you're titrating, you have to make sure that the golden brown color of iodine fades to until it's pale yellow, right, or very light yellow. I use the word pale yellow. It's after we got into that point, that's when you cannot add your starch. Then you get blue black. Then you 1 or 2 drops of the thiosulfate by constant shaking. We change it from blue black to colorless. Remember, you don't add your starch like you do your normal titration, acid-base titration. No. For this titration, this is an iodometric titration. It's an example of a redox or redox titration, the redox titration. So you don't put your starch immediately, and there are reasons for that. We'll answer that question at the end of this calculation. You make sure that as you start titrating, you start adding the thiosulfate from your burette into the conical flask containing your iodine solution, which is golden brown in color. You shake until the solution fades from that golden brown color to pale or light yellow. You stop. You have to be very careful before you add your starch, which you turn it to blue black. Then you continue 1 or 2 drops with constant shaking. We change it from blue black to colorless. That's the end point. So that's how you get all these figures. You do it for the first, you run second, you run third. At the end of the day, you notice that these 3 values, you can use these 3 values because they are not, the difference between each of these values are not more than 0.2. If it's more than 0.2, you can't use it. That means you have to run more. So as usual, you add the 3 together, divide by 3, then you get the volume of acid used, which is here I'm using 12.43. It doesn't mean this is one you're going to use that day. It's going to depend on what you carry out and your endpoint in your school. That will determine that. Remember, if you notice, this is into 2 decimal places. Everything here is to 2 decimal places. 0.00, 12.40, decimal place. That's 2 numbers after the point, 2 decimal places. Everything has to be uniform, right? To this, they have to be uniform, 2 decimal places. So after this now, we can now calculate for other things. So from your question, the equation that was given so the first question there was that it said you should calculate the concentration of in mole per dm cube. So, but remember your A is the thiosulfate, and we're only giving the mass concentration of A. Remember, mass concentration is the same thing as gram per dm cube. You can check back your questions to see. So remember, mass concentration, not to calculate the mole concentration, and we are giving concentration. So we just use this formula. Concentration of mole dm cube is equals to the mass concentration over molar mass. we were given the mass concentration as 15.8. That's for thiosulfate. Then the molar mass of thiosulfate, you can calculate that one. So let's calculate the molar mass of sodium thiosulfate. Remember, it's Na2S2O3. That is 23 times 2 plus 32 times 2. That's 16 times 3. So at the end of the day, we are having 46 plus 64 plus 48. So we are getting 158. So this is the molar mass for sodium thiosulfate. So now I need to mass concentration from your question. We're giving concentration to be 15.8. You can check back. So to calculate the concentration of A in mole per dm cube is equals to, that is 15.8 over 158. So at the end of the day, you are getting 0.1 mole per dm cube. So this is the concentration of A in mole per dm cube. So let's find the second question, concentration of the iodine in B in mole per dm cube. From your equation, you can see that you can check that the mole ratio for the thiosulfate is 2, while the one for the iodine is 1. And so we know this, we know this, we know this, or this. So we just substitute. So Ca, we just calculated Ca to be 0.1. Va, the volume of reduced, 12.4. Then Cb, we are looking for. Then Vb, the volume of pipettes, we use 25 over the mole ratio. Na is 2 and Nb is 1. So multiply the, you should have something like this. That is 0.1 times 12.43 over 25 times 2. Another day, you should get 0.02486. That is approximately 0.025 mole dm. So this is concentration of I2 in B in mole per dm cube. So the third question is, they say calculate the percentage by mass of iodine in the sample. Percentage by mass of iodine. Percentage by mass of iodine in the sample we are calculating next. So to calculate the percentage by mass of iodine in the sample, we are using mass of pure or mass of impure times 100 over 1. This mass of pure, I'm actually referring to the mass concentration of, of the iodine. Remember, we were given the mass concentration of impure iodine in the question to be, if you check your question back, to be 9.0 gram per dm cube. That is what we were given from our question. So we have to calculate the mass concentration of iodine by using this formula, so that we know this already. We have to calculate for this, right? Concentration of iodine. So we are going to use the normal formula. Nice. Concentration the mass concentration times molar mass. We know the concentration per dm cube. We just calculated it In fact, our value was 0.02. So you have to, of course, the molar mass of iodine is 127. Is in your question, but iodine is the atomic, so you have to say 127 times 2. So that you get 154. Sorry, that's the 127 times 2. Okay, so we've calculated this one. Molar mass of iodine is 127. Since it's the atomic, times 2, you should get 127. 7 times 2, 254. So we know this one, we just calculated it, 0.025 times 254. Should get 6.35 gram dm cube. So this one we just calculated is the mass concentration of the pure. The mass concentration of impure is given in your question as 9.0 gram per dm cube. It is stated there. It's stated in your question. So you just put this value here and the other value here to calculate the mass percentage of iodine in the sample. Remember, this is also like saying calculate the percentage purity of iodine. Question, instead of asking you to calculate the concentration of iodine in the sample, they will ask you for the percentage purity. This is the formula I'm still going to use. Mass concentration of pure over impure times 100/1. The impure will be given to you in your question. While the mass concentration of pure, you can calculate it from the concentration of dm cube. So let's put these values here. So it will now be the mass concentration of pure is 6.35. 6.35 over, so the mass is 9.0 times 100/1. At the end of the day, you should get something like 17.6%. 70.6%. So this is the mass concentration of iodine in the sample, or the percentage purity of iodine. Just for instance, maybe you might be asked to calculate percentage impurity. When you are asked to calculate percentage impurity, just know that percentage impurity is equals to 100 minus percentage purity. What it means is that if in this question you're asked to calculate the percentage impurity, you subtract 100 from this value, you get your percentage impurity. Understood? So these are follow-up questions. Look at this question. Follow-up question. Give reasons why the starch indicator was not added to the titration mixture at the beginning of the titration. So the starch wasn't added at the beginning of the mixture because it will form a complex with the iodine, or you can say it binds too strongly with the iodine, which will give an inaccurate result. So that is the reason why the starch indicator was not added to the titration mixture at the beginning of the reaction or the titration, because it will form a complex. That's the reason why starch is not added to the titration mixture at the beginning. It will form a strong complex, or it will bind too strongly to the iodine, thereby giving an inaccurate result. See this one. Why is starch indicator added close to the endpoint to give an accurate result? Right? I said, why is starch indicator added close to the endpoint to give an accurate result? Then this other question: what happens at the endpoint? The color changes from blue-black to colorless. What happens at endpoint? The color changes from blue-black to colorless. Then I might want to add another one, just in case you're asked, why does starch solution has to be freshly prepared? Just in case you're asked, why does starch solution has to be freshly prepared? It is because it deteriorates quickly on standing. I said, if you're asked, why does starch solution has to be freshly prepared? The reason is that it deteriorates quickly on standing. So that's for the titration. So let's do the salt analysis briefly. Alright, for your salt analysis question, I'm going to draw this question because from your specimen we were given moles salt, MOHRS, moles salt. That is ammonium ferrous sulfate. That is NH4 bracket 2 FeSO2 SO4 bracket 2 then CH2. Ammonium ferrous sulfate is a double salt. Double salt, when it dissociates, they give 2 cations and 1 anions. So from the question, from the salt, you notice that both the ion and the ammonium, they are cations, while the sulfate SO4 is anion. That by the wayside. Anyway, so normal procedure. I said C plus the seed water. It is expected that C dissolves to form a light green solution. So when this happens, you know that C is soluble. Then I said plus litmus. So it's expected to turn litmus paper is expected to turn red. So the difference that C is acidic. Then you might be expected to divide this solution into 3 portions. The way I did is I said the first portion of C plus barium chloride. When that happens, a white precipitate will be formed. The difference there will be CO32 minus, SO42 minus, or SO32 minus. Then plus dilute HCl. When this happens, the precipitate is insoluble. Then difference will be SO42 minus confirmed. Here you put CO32 minus, SO42 minus, SO32 minus present. But when you add dilute HCl and the precipitate is insoluble, you will confirm SO42 minus. That's why I put SO42 minus confirmed. If you don't want to use precipitate is insoluble, you might put no visible reaction. Okay, the other ones here, I'm saying second portion of C plus sodium hydroxide plus heat. Of course, when this happens, you can see that the inference here is that a gas is involved with characteristic choking smell, turns red litmus blue, and forms white dense films with conc HCl. So the difference is that the gas is ammonia from ammonium ion. So take note, I added these parts. I did not add them in the test, just in case after heat they might tell you that okay, test with litmus paper. So here I can put plus litmus paper. Then before I put that it turns red litmus paper blue. They may also say okay, test with conc HCl stopper. You can also put the information here. Then before you write the observation, then this will be the inference. That is for the second portion of C. The third part now, I said third portion of C plus sodium hydroxide in drops. So when that happens, a green precipitate will be formed. Then here you can say the difference. Here you can say that ion 2 is present. Then plus in SS, you can say no visible reaction, or it is insoluble in SS. But maybe you might be asked to what happens when this solution is allowed to stand for some time. When that happens, you notice that ion 2 will be oxidized to ion 3. Then the color now will not change from this green to reddish brown. So I didn't put it here. I'm just saying, just in case you're asked, what happens when this solution is allowed to stand for some time? What happens is that ion 2 will be oxidized to ion 3, and so the color will change from green to reddish brown. So the difference, you will now put ion 3 plus present. So I'm going to add this last test for this sort analysis. So I decided to add this one. So I'm going to assume that the sample was divided into 4 portions. So yeah, I'm saying fourth portion of C plus acidified K2SO2O7. We know that this is an oxidizing agent, right? The color is orange. So I'm saying fourth portion of C plus acidified K2SO2O7. The observation here, I said K2SO2O7 is decolorized, meaning the color changes from orange to green. Before you add the solution, the color of this sample C was faint or light green, but when you now add this acidified K2SO2O7, the color turns to slightly darker green. But when reporting it, the observation, putting in this form that this K2SO2O7 is decolorized, then the difference will be that a reducing agent is present. It's only when a reducing agent is present that is when this color can change. Otherwise, it will not change. So once it changes or is decolorized, you know that the inference is that a reducing agent would be present. So that's all for this video. Of course, for your revision, once again, this is not the exact question that will come out. This is just to help you out. You still have to do your own part. So if you enjoyed the video, leave a like and subscribe. Thank you.